Hey everyone, welcome back to another video by Camroom 5. In today's video we are going to be talking about catalysts. We will try to answer 4 questions. The first of which is, what do they do? The second question about catalyst would be how they do it. The third question that we seem to be addressing today is, do they participate in a reaction? And the fourth question is, what's activation energy? So catalysts, they speed up a chemical reaction. When they speed up a chemical reaction, remember, they are not increasing the product. They just make sure that the reaction takes less time. So the same amount of product will be made, but the reaction takes less time now. They decrease the activation energy. Is that how they do it? So they decrease the activation energy value for a reaction. Remember, they are not providing the energy, they are decreasing the requirement of activation energy. They provide an alternate route with lesser activation energy. So the same reaction at the same temperature would involve less activation energy. Do they participate? Yes, they do participate in the reaction. They participate in reaction. But they are not used up. But they are regenerated by the end of the reaction. So they are regenerated by the end of reaction. So they're regenerated, which means their amount remains constant. You can't expect the catalyst to be used up. Their amount remains unchanged. The last question is, what's activation energy? It is the minimum energy required for the reaction to happen. It is the minimum energy required by particles to react. Because for reaction, their collision isn't enough, right? It is a minimum energy for a collision to be successful. What do we mean by that? Particles collide continuously, but if they have the activation energy value, only then it would be successful. To understand this, we are going to dig in deeper into the concept of activation energy. Activation energy will be related here with the concept of Boltzmann curve. When we talk about Boltzmann curve, we are going to be talking about normal distribution. Imagine you have 15 molecules of hydrogen and 15 molecules of chlorine. They want to make hydrogen chloride. The red molecule is the hydrogen and the green one is chlorine. How many molecules do we have in total? So that is going to be 30. Now what we are going to be doing is, we are segregating these molecules on the basis of energy. I have energy range in joules, and then I have how many particles have that much energy, which is the frequency of those particles. It is like basic statistics here. Imagine I'm talking about 10 to 20 joules, 21 to 30, then 31 to 40, then continuously I am making a range of energy like 71 to 80 joules, 81 till 90 joules, and 91 till 100 joules. Now I have a single particle which has energy between 10 and 20 joules. 2 molecules have energy between 21 and 30, 3 with higher energy, 5 has energy between 41 and 50, 7 have energy between 51 and 60, so apparently that's the most common energy. Only 6 particles with energy between 61 and 70. And using the similar pattern, you can see very few particles have high energies. If I make a graph of this, I'm going to be putting the energy values on the x-axis. And on the y-axis, I'm going to be putting the frequency, or you can say the probability of particles. It means that out of those 30 particles, how many have 10 joules, how many have 20 joules, how many have 30 joules, and so on. For example, between 10 and 20 joules, only a single particle has that much energy. 2 particles have between 20 and 30, 3 particles have between 30 and 40, 5 particles have between 40 and 50. There are 7 particles which have energy between 50 and 60, so apparently that seems like the most common energy, because most particles have this energy. Then there are few particles with higher energies, like only 3 particles with energy between 71 and 80. Then only 2 particles with energy between 81 and 90, and like single particle between 90 and 100. That's a normal distribution. We can also call it the Boltzmann distribution. So in normal distribution, the most common value is obviously possessed by the most particles or most individuals. You can see there are 7 particles which have energy between 50 and 60. So apparently 55 seems to be the most probable, most common energy. But that does not mean the highest energy, it means the most common one. Because the most particles out of total have this energy. You can see there are very few particles with low energy values. Like there are very few particles with energy between 20 and 30, and even fewer particles with energy of 20 or even 10. And at the same time, there are also very few particles with high energy values. Like 80 and 90 is not a very common value. Only a very few particles have it. For those who study biology, that's exactly continuous radiation. Now going into the detail, imagine these particles want to react, but the activation energy is 80 units. Imagine the activation energy for this reaction was 80 units. Now only the particles with energy equal to or higher than 80 can properly react. So we don't care about particles with low energies, we care about particles which have high energy, like these ones. These 2 particles with energy of 90 almost, and there's 1 particle between 90 and 100. These particles have energy which is more than or equal to activation energy. So their energy is either equal to or more than activation energy, and that is the criteria. This red region on the curve shows the proportion of the particles which qualify. Now with a catalyst, let's suppose the activation energy is 60 joules, so more particles now qualify for the same reaction. I'm not changing their energies, but now total has increased. First the total was 3, only 3 particles had energy more than 80 or equal to 80. Now there are more particles. Now almost 12 particles are there which have qualified. These 6, 3, 2, 1, they all qualify. This green region shows all particles with energy more than or equal to activation. To summarize, now we have total of 30 particles. 15 were hydrogen, 15 were chlorine. How many particles had energy more than or equal to activation energy, like in normal conditions? So 80 joule was the activation energy requirement. Only 3 particles had energy equal to or more than activation energy, which is just 10%. So 90% were colliding but not reacting actually. In the presence of catalyst, the energy more than or equal to activation energy scenario was changed. Now the activation energy was 60 joules. And 12 particles had energy more than or equal to activation. That is 40%. So now 40% particles qualified for the reaction. Your explanation will involve more particles have energy equal to or more than activation energy, equal to or more than activation energy value. So we are not increasing the energy of particles, we are decreasing the requirement. So their collision are successful now. And that is the main thing that a catalyst does by increasing the proportion. So in today's video we answered few questions about catalysts, and then we tried to talk about the Boltzmann curve and put activation energy over there. Stay tuned guys. Thanks.